So far in 2 dimensions, we've only looked at one property of a wave, that property being reflection. And that's a property that when a wave encounters a boundary, some of the energy bounces off and returns into the same medium and changes direction. So the next thing that we're going to look at is, well, what happens if that wave encounters that boundary, but rather than bouncing off that boundary, goes through the boundary into the new medium? So that's the idea here. First, I'm going to define a word. It's not a property of a wave, but it's an idea called transmission. And this is just very simply a wave changes medium. And if a wave changes medium, that must mean it went through the boundary. Now, let's just think about a time when that can happen. An easy example is to think about sound waves. If you can hear a sound wave through a wall, that sound wave transmitted or experienced transmission through the wall. But it doesn't really have to be all that formal. In water waves, which is what we're going to be looking at in the videos later, the main factor that affects the speed at which a wave transmits is the depth of the water. And we'll see that in the video. And so if you have a water wave going from shallow to deep or deep to shallow, that functions like a transmission because there's a change in the medium. Okay, so if a wave goes through the medium, it goes through the boundary, it changes medium. So what does that mean if it changes medium? The number one thing that happens during a transmission is, therefore, the wave's speed must change. Right? Because if a medium is the only factor that determines the speed of a wave, if a transmission is defined as a change in medium, then the speed must change. But we should note then, the frequency does not. Why not? Well, because the source didn't change. Okay? So the speed changes, the frequency doesn't, but if the speed changes, the wavelength must change. Because if we look at the equation, v is equal to f lambda, if f is remaining constant, therefore I can say there is a direct relationship between the speed and the wavelength. So whatever happens to the speed is what happens to the wavelength. If the speed doubles, the wavelength doubles. If the speed halves, the wavelength halves, because these are in a direct relationship. Okay, so that's a transmission. Now we're going to be looking at some very specific transmissions, and that's going to comprise the second property of a wave. But let's imagine that we have a bunch of wave fronts coming in. All right, so here we go. I'm just going to draw some wave fronts coming in. And let's say that there's some sort of boundary here between two media. And so usually the example I use in class is, imagine we're driving on the pavement here and we're going into the gravel lot. So what happens as you're driving on pavement and then you go into the gravel lot? Well, on pavement, you're moving faster. Here on the gravel lot, you're going to go slower because of all those loose rocks. You don't have as much traction. So here I'm going faster. Here I'm going slower. So if I draw a ray to represent what's happening to the waves there, boom, there you go. Now notice here, what is the angle of incidence for this wave? And if you said that 0 degrees was the angle of incidence, you are correct. Because remember, we always care about the normal line. So if I draw a normal line here, my ray is coming in along the normal line, right? And so I'll just say theta 1, the angle of incidence here is 0 degrees. So what's going to happen here? Very simply, our wave is going to continue on in a straight line. There's no reason for it to change, and we'll talk about why a little bit later. But if it went from faster to slower, what's going to happen to the wavelength? If you said the wavelength gets shorter, you're right. So if I were to draw a sampling of what the wave fronts might look like now, boom, it might look something like that. So you have a longer wavelength, a shorter wavelength, faster, slower, but the frequency here and the frequency here would be identical. Now, what about the amplitude of these waves? Well, the amplitudes of these waves would be, so let's say if the amplitude of this is A initial and this is A final, we would find out that A final is always less than A initial. Well, why is that? Well, I'm not showing it, but some of the wave energy when it encounters this boundary is going to reflect, right? And then some transmits. And so since some of the energy transmitted, some reflected, this has got to be less than what this is. So this is what the wave looks like if it slows down. If it speeds up, we can come over here and draw a very similar sort of picture there, and we'll keep it so that the wave is incident at a 0 degree angle. All right, let me draw my boundary in here as well. Boom, the red lines are boundary. I'll draw in our incident ray, which would be perpendicular to the incident wave fronts. Right, once again, theta 1 is equal to 0 degrees because I'm coming in along the normal line, which I've just dotted in, and here would be my transmitted wave there. But what do these wave fronts look like? Well, if I'm going from slower to faster, say I'm going from the gravel lot to the pavement, we would find out that the wavelengths would extend from there, right? Because I sped up. So if this is larger in the new medium, that's got to be larger since the frequency is the same. So that's the basics of what's going on. So now let's look at this and our new property of our wave. And the property is going to be called refraction. So reflection, refraction. Both happen when a wave encounters a boundary. So we're going to talk about that transition going from the pavement to the gravel lot, or the gravel lot to the pavement again. But we're going to do this a little bit differently this time. So once again, here's my boundary. Okay, I'm going to draw in the normal line to start here. Boom. Okay, normal dotted line goes through the boundary. There it is. Notice I drew a solid line for the boundary, always a dotted line for the normal. So what we're going to do here is, rather than have the wave fronts be parallel to the boundary, I'm going to have my wave fronts be at an angle to the boundary. Okay, so let's say these are my wave fronts. That means my incident ray is going to look like this, perpendicular to there. Now, I could draw any of them. I'm going to happen to draw the one that goes to where I happen to draw my normal line. Really, what I should have done here is draw the wave fronts, drew the incident ray perpendicular to the wave fronts, and wherever the incident ray encountered the boundary, that's where I should have drawn the normal line. So the normal line should come a little bit later. But let's do this again, where I'm going from a medium where I'm traveling faster to a medium where I'm traveling slower. And I want you to think about that transition from the pavement to the gravel. So let's pretend here that my iPod Nano is a car. And we're looking overhead at this, as you are. So that means that there's wheels on the car here, 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 and here, right? So let's see what happens. If I were to come in along the normal, a 0 degree angle of incidence, boom, notice here that the two wheels simultaneously cross over the boundary, right? So these wheels at the same time slow down. But watch what happens here if I come in at an angle. Boom. This wheel is in the material where I'm going slower, and that wheel is in the material where I'm still going faster. So what happens to this if that's going slower than this side is? And if you said that the car turns, you're right? Because this is what's going to happen. This side slows down, that side does not slow down until it crosses the boundary, and then it does. And you can see what happens is the wave changes the direction that it propagates. Okay, so let's draw what that ray looks like, and we're going to call that ray a refracted ray, because that's what refraction is all about. The refraction is the change in the direction of energy transmission. Now that sounds a lot like what happens during reflection, right? So what's the difference? When a wave passes obliquely, I'll explain what that means in a second, from one medium to another where the speed changes. Now that last bit where the speed changes is redundant because if I'm changing medium, I should be changing speed. So let's deal with that notion of obliquely. Well, notice here in our previous example, we had a wave passing from one medium to another, but I didn't say anything about obliquely here. Obliquely is just a fancy way of saying at an angle, right? So since this makes a 0-degree angle to the normal, and this does not, this would be obliquely. And so if I call this here theta 1, the angle of incidence, we're going to call this here theta 2, the angle of refraction. Okay. And notice those two angles are not the same, and that's why we say there's a change in direction. But what causes refraction? Well, I think we can see what causes refraction if we look at a wavefront that part of it is on one side of the boundary, but part of it is on the other side of the boundary. Because that's what's going to happen here, is that if I was drawing wavefronts here, and this will be clearer when we see this in the video, is that because the same different parts of the same wavefront change speed at different times, that's what causes this change in direction. So different parts of the same wave change speed at different times. Okay, that's the reason why refraction occurs. Now here where I slowed down, a couple of things. If I call this medium 1 and this medium 2, clearly V2 is less than V1. A couple of other things, therefore lambda 2 is going to be less than lambda 1. We showed that in the previous page. But if you notice here also, theta 2 is less than theta 1. The way we're going to describe that is when a wave slows down, the ray bends toward the normal. And there we go. That's refraction. Now, we could also do a refraction, but instead of the wave slowing down, the wave could speed up. So let's draw once again. I'll do this the right way this time. We're going to draw our boundary. I'm going to draw some incident wavefronts, and just so you can see it coming from a different direction, boom, let's draw them coming from this direction. Cool. I'll draw my incident ray now. And where my incident ray intersected the boundary, that's where I sketch in my normal line, boom. And so if we think about that in terms of the car analogy, we have the car going here, but now this gets into the new medium before this one. We said it's going to speed up, so this is faster, that's slower. That means this wheel is going faster than that one, and so it turns this way instead, and off it goes. You can see once again the direction of energy transfer changes. Okay, boom. And if I wanted to draw what some outgoing wavefronts from that might look like, they might look like that, right? Once again, theta 1, theta 2, and when you slow down, right, we just not slow down, we sped up, speeds up. V2 is larger than V1, there lambda 2 is larger than lambda 1, and therefore theta 2 is larger than theta 1, right? Or another way to say this, that the ray bends away from the normal line. Now, you might wonder, is there a mathematical relationship between these two? And the answer is going to be yes. We'll look at that in a later unit. But right now, we're just going to learn the trick, or the patterns of what happens, that during refraction, we're going to get a change in the direction of the energy transfer. And then if I speed up, in this case, it bends away from the normal. The refracted ray bends away from the normal. And if it slows down, it bends towards the normal. And if it goes along the normal line, it doesn't bend, which is why not all transmissions are refractions, but all refractions are transmissions.